Welcome to the problem-solving session for Chapter 27. Let's begin with our first question. Here, we're told to calculate the resistance of an aluminum cylinder which has a length of 0.1 meters and a cross-sectional area of 2 e to the minus 4 meters squared. Then we're to compare that value of resistance with another aluminum cylinder of the same dimensions, but instead made out of glass, and we're given the resistivity for that type of glass. So let's first work out the value of R for our aluminum cylinder. Well, you can see that we need to have the value of the resistivity of aluminum in order to perform this calculation. When we go to our table in the textbook, we see that the resistivity of aluminum at the reference temperature, which by the way is the temperature for which we are calculating the value of resistance in this case, since we have not been told what the value of resistivity is, we have to assume that it is at the reference temperature. So we have 2.82 e to the minus 8 ohm meters times L, 0.1 meter, divided by the cross-sectional area, 2 e to the minus 4 meters squared. When we plug in the numbers in the calculator, we get a value of 1.41 e to the minus 5 ohms, which you can see is a very small value of resistance. If we now proceed to calculate the same resistance, well, I should say, the resistance for the same dimensions of length and area, but this time for the material which is glass, we find once we plug in our numbers, our resistivity is very much higher. In fact, 18 orders of magnitude higher. It's 3 e to the 10 ohm meters times 0.1 meter of length divided by 2 e to the minus 4 meters squared. And we get a value of 1.5 e to the 13 ohms, and you can see the resistance is much higher. The resistance in this case would be 13 plus 5, again 18 orders of magnitude higher. Next question. Here we are told that a thermometer used to measure large values of temperature is made out of a resistor whose resistance changes with temperature. This thermometer is made up of specifically platinum, and we know that it has a resistance of 50 ohms at the reference temperature of 20 degrees Celsius. It says this thermometer, in other words, this resistor, is going to be placed inside a vessel that contains melting indium. And we see that the temperature, or rather the resistance of the platinum goes up to a value of 76.8 ohms when this happens. Well, of course, a thermometer which is immersed in this case, liquid indium, is going to be at the same temperature as the liquid indium is. And so we're asked to determine the temperature of the melting indium, which is, of course, the temperature for which the platinum in our resistance thermometer goes up to a value of 76.8 ohms. Well, one thing that we need is to know what the alpha, the temperature coefficient, is for platinum. And when we look it up in the table, we see that it's 3.92 e to the minus 3, minus 3, 1 per degree Celsius. So in other words, the platinum undergoes a change in resistance in this form here for this number for every degree Celsius. So the resistance changes by this value per degree Celsius. Well, we have our expression for the change in resistance as the resistance at the reference temperature times 1 plus alpha multiplied by the change in resistance. And so we can solve for delta T, the change in temperature, by algebraically isolating our variable, R final, divided by R initial, minus 1 times 1 over alpha. And we come over here, substitute our numbers, 76.8 divided by 20 minus 1 times 1 over 3.92 e to the minus 3, 1 per degree Celsius. And we get a value of delta T, which is 724 degrees Celsius. But of course, we were asked to determine T final, and so T final minus 20 equals 724, so it must be that T final is 744 degrees Celsius. Next question. Here in question 3, we're told to calculate the resistance per length of a nichrome wire that has a radius of 3.21 e to the minus 3 meters. And then we're told that a potential difference of 10 volts is going to be applied to 1 meter length of this wire, and we want to calculate the current through the wire. So first, resistance per length will be resistivity. In this case, it'll be nichrome, so we'll have to look it up, divided by the area, which for any wire, the area, the cross-sectional area, is pi times r squared, because it has a circular cross-sectional area. When we look up the value, the resistivity for nichrome, we get 1.5 e to the minus 6 ohm meter from our table at the reference temperature, divided by pi times 3.21 e to the minus 3 meters, and of course we must square this. Well, I get a value of 0.0463 ohms per meter. Well, in part B, we want to calculate the current through 1 meter length, which means that if we take R per length and we multiply this by 1 meter, well, of course, we get the total R, which is just 0.0463 ohms. Using Ohm's law, we can determine the current I as the ratio of the potential difference divided by the resistance. Well, here again, 10 volts of potential difference divided by 0.0463 ohms gives us a very large current of about 216 amps. Next problem. Question 4 says we have an electric heater which is going to be subjected to a potential difference of 120 volts. The total resistance of the wire that makes up the heater is 8 ohms, and we want not only the current that passes through the heater, but also the power rating of the heater. Well, to get the current, we simply use Ohm's law, delta V over R, 120 volts divided by 8 ohms. That gives us a current of 15 amps. 15 amps. Power can be calculated. Remember, we have 3 ways to calculate it, but I will go ahead and just use the value of the current, which we just obtained, I times delta V, and that gives us 15 amps times 120 volts for a power rating of 1800 watt or 1.8 kilowatt. Could we have used the expression I squared times R? In other words, would 15 amps squared times 8 ohms given us the same result? Could we have used delta V squared over R? In other words, 120 volts squared divided by 8 ohms? Check it out. See if we don't get the same result, because these two expressions have been derived using Ohm's law. Next question. Question 5 tells us to compute the cost per day, or for 1 day, to operate a lamp that draws a current of 1.7 amps from 110 volt source. And we're told that the cost of energy is 6 cents for every kilowatt hour used. Well, the first thing we better find out is what the power rating is for this lamp. I times delta V. We have 1.7 amps times 110 volts. Well, this gives us 187 watts for the lamp. And of course, we want to write this as 0.187 kilowatts. Now, what we're really looking for is the quantity of energy, which means we have to take this power multiplied by the time. Well, the time is 1 day, which is 24 hours. So 0.187 kilowatts times 24 hours tells us that the quantity of energy that we use in 1 day is 4.488 kilowatt hours. Now that we know this, we're ready to calculate the cost. And remember that the cost was 6 cents or $0.06 per kilowatt hour. When we take our kilowatt hours and multiply by the 6 cents, we find that, of course, our units of kilowatt hour cancel. It only costs us $0.27 to operate this lamp per day. In other words, 27 cents. Not a lot of money, is it? But of course, that's not always true, because we are always hit with the cost for the taxes. And so this is just one lamp. When you consider that you operate so many appliances over the course of 1 day, the cost can really add up. Well, this concludes our problem-solving session for Chapter 27. Until next time.